There we go. All right, so we are live, everyone. My name is Jesse, and I am with Exploring by the Seat of Your Pants. For those joining us for the first time, we are all about bringing conservation, adventure, and science into classrooms around the world. And of course, there are no real classrooms around the world right now. All of you are joining live on YouTube, so thank you so much for tuning in, and we really appreciate you joining us today. Again, we're going to be having sessions every day, many sessions with all manner of scientists, so keep checking us out over the weeks and months to come. Today, we are joined live in London, Ontario, Canada, by Dr. Matthew Cross. So he is a space engineer. He works on rovers, he works on satellites. He has worked with the European Space Agency, the Canadian Space Agency, and more. One of the coolest jobs in the world. So we're going to turn it over to Matt today, who's going to explain a little bit about the work that he does and inspire us to get a little excited about some of the cool things that are happening in space programs across the globe. So without further ado, thank you so much for joining us, Dr. Cross, and take it away.
All right, thank you. So I will just share my screen and bring up my presentation. All right, and can you see everything, Jesse?
Right now, yeah, we got your main slide in the middle and your other slide in the left. It's not filling the whole screen yet, though. Sorry. See, it worked in testing minutes ago. This is having fun. No, still not liking it. Sorry, Matt.
No worries. I will just try this again.
We'll get there eventually. I'm excited.
I will reset that.
And take two. For anyone tuning in too, while we're getting the slides up, do check out Western Space's programs with us over the last few months. We've done many with them, some really, really fantastic science. And so it's exciting to share even more. So, wants to work. Really does. Oh, there we go. Perfect.
Perfect. Excellent. Great. So hello, everyone, and thank you for joining me today. So I am Matt Cross, and I'm going to be talking about space engineering and some of the things that I do. And so first off, when we think about space exploration or astronomy or planetary science, we often see really cool pictures like these. So we can see close-up pictures of Pluto. We see pictures that astronomers have taken of distant nebula. And we sometimes don't think about Earth when we talk about planetary science. However, we're still learning about the Earth from space. And we also get pictures from the surface of other planets, such as pictures from Mars. Now, behind all of these great pictures are different kinds of space systems. So the New Horizons spacecraft flew past Pluto. The Spitzer Space Telescope captured images of stars and nebula. The Earth observation satellites, such as Landsat, take pictures that help monitor Earth's environment. And the Curiosity rover is driving across the surface of Mars. So scientists ask questions like, was Mars ever habitable? And then engineers help design space systems, such as rovers, that can then help answer those questions. So I'm Matt, and I do space engineering. So just a quick introduction and a little bit about myself. I grew up in Nanaimo, British Columbia, so that is home of the Nanaimo Bar. I studied aerospace engineering at Carleton University in Ottawa. And one of the projects that I worked on was the CAP-VIC rover for the Canadian Space Agency. And so that's a picture of me sitting next to the CAP-VIC rover. I also worked at the European Space Agency for a couple of years as a systems engineer. And I worked on the European Student Moon Orbiter project, which is where I gained a lot of my more practical space engineering skills.
Matt, you appear to have frozen for a second. See if we can get you back. We've had all the tech difficulties today. It keeps it exciting. Well, All right, so Matt's cut out for just a second, and we're hopefully going to get him back in a second. While he's gone, and I've sent him an email to see if we can get him back in. Just a quick note for our people tuning in live. Again, we've done many sessions with Western Space over the last few months, mainly highlighting the Canadian Space Agency's Junior Astronauts program, which I think Matt's going to touch on a little bit later in this presentation. But oh, he's gone now entirely. Okay, we'll hopefully get him back in a second. So the Junior Astronauts program, really, really exciting Canadian Space Agency initiative. And this is something that you guys can look up online, take part in some really cool activities while you're stuck at home, and more. We're also going to be doing more sessions with Western Space. So this is London, Ontario's fantastic astronomy program with some really, really cool people. And Matt is back. So we're going to talk about that. Hey, the
All
audio.
right, let's see if
anything that can go wrong will go wrong today, but that's okay.
All right, we will get back into this. So let me get back into my presentation. And now, where did you last hear from me?
We last heard from you. You had just been started to talk about this work that you've done on some of the satellites. We hadn't got into CubeSats yet.
Okay, so yeah, so just finishing up about me. So I am managing a CubeSat project at Western, and that's where we're going to continue on to next. So what is a CubeSat? Well, a CubeSat is a miniature cube-shaped satellite, and there are many orbiting the Earth high above us. Just like any satellite, CubeSats are custom built to the specific requirements of their mission and have at least three things in common. So they have an antenna and radio communication system, which sends and receives information to and from Earth. They have a power source, like a solar panel or simply a battery. And they have a computer, which executes instructions to ensure proper functioning of the satellite. The main cubic structure is made of aluminum and serves to hold all of the components along with others, such as cameras, sensors, or scientific payloads. In addition, antennas and solar panels can be installed on the exterior of the structure. A standard 1-unit cube is a little bit bigger than a Rubik's Cube, and many cubes can be stacked together. Now, compared to many satellites, CubeSats are quite small. So a large satellite, such as Canada's RadarSat-2, is over 1,000 kilograms, or about the size of a rhino. CubeSats are much smaller and weigh somewhere between a duck and a raccoon, depending on how many units are stuck together. Now, because of their size, CubeSats have many advantages. They are simpler than bigger satellites and can be built faster using simple standard parts available off the shelf. Their shorter mission life makes them more manageable to operate, and they burn up in the atmosphere upon re-entry, so there is no debris left in orbit, which can become a problem if there's too much debris floating around in space. So I'm leading a group of students to design, build, and test a satellite that will be launched into space. We are partnering with the Nunavut Arctic College, and they have named the CubeSat Ukpik-1, which is the Inuktitut word for snowy owl. Our CubeSat is 2 cube units, which is a bit bigger than a Kleenex box. The students will also be operating the CubeSat, which means they'll be in our mission control room sending commands to the satellite. Now, what will Ukpik-1 do? It's going to use a special camera system to take spherical VR images so that you'll be able to wear a VR headset like an Oculus Rift and see what it's like to be in a satellite in low Earth orbit. So you might look down and see the Earth, and then look up and see the space station, and then look behind you and maybe even see the moon. So it's pretty cool and amazing to see what our students are able to do while learning about space engineering. Now, another project I'm working on is the Barefoot Rover, and that's with the NASA Jet Propulsion Lab. So what is Barefoot Rover? Well, imagine yourself walking around in your bare feet. Maybe you feel soft carpeting beneath you, or maybe it's hardwood or vinyl flooring, which feels very different than carpet on your feet. Now imagine what happens when you step on some Lego. It's sharp, and you can definitely feel it. Now imagine yourself walking outside on grass and how that feels very different compared to walking on concrete or dirt. Now, you can close your eyes and still get a sense of what you're walking on. So your bare feet tell you a lot about your environment. So what if we could give rovers the same sense of touch? And that is what the barefoot wheel is trying to do. There is a special pressure pad that wraps around the wheel, and the pressure pad is able to sense what kind of surface the wheel is driving over, kind of like when you walk in your bare feet. Now, in order to train the wheel to know what it's driving over, we have to drive the wheel over many different types of surfaces and do that many, many times. In fact, there have been over 1,000 training runs. So all of that data that we collect helps to train the wheel to know what it is driving over, such as rocks or sand. And so here's a couple of pictures, and this is what the wheel feels and how it looks like in the data. So this top picture shows what the wheel feels when it goes over a rock. And so the rock concentrate over a smaller part of the wheel, kind of like when you step on a small rock or a piece of Lego. The bottom picture shows what the wheel feels like when it's going over sand, which is more spread out over the wheel compared to the rock, kind of like when you walk on a nice smooth surface. So rovers will then be able to know if what they are driving over is safe based on its sense of touch and feel. The other project that I'm working on is to help improve autonomy of rovers that will go to the moon. Just as people need to practice and practice and practice to safely operate a rover, rovers will need lots and lots of training in order to learn and become more autonomous. It's not very easy to go to the moon to do that. So we take rovers into the field on Earth to take lots of training data. So I spent a couple of weeks at the Canadian Space Agency driving our rover over their Mars yard to take lots of data to train the rover using machine learning. What we are trying to do here is to help teach the rover what an interesting rock or feature is, and then find a way to help a rover learn that on its own when it gets to the moon. The more the rover can do on its own, the more science we can get back on Earth. So we're trying to do that with both pictures and with LiDAR, which uses lasers to create a 3D model of its surroundings. The advantage to LiDAR is that it creates a 3D map without needing any sunlight. And there are parts of the moon that never see the sun, which are areas that scientists are quite interested in. So we are trying to help train a rover to find interesting features using LiDAR so that future moon rovers will know what to look for. Now, before we can send rovers to other planets, we have to practice working with rovers on Earth. Operating a rover on another planet is very complicated. It takes a big team of scientists and engineers to make safe operations of the rover and to make sure it can collect pictures and science data to send back. So how do you make sure you can safely operate a rover? Well, it takes lots of practice and training. And we can practice that here on Earth with rovers such as MESER, which the Canadian Space Agency uses to practice how to operate a rover mission. In fact, any space mission requires a lot of practice to make sure you know how to operate the spacecraft. If something goes wrong, no one can go and fix it. So we have to practice, practice, and practice. And most importantly, space engineering requires a lot of teamwork. Lots of engineers work together with scientists to help make space exploration possible. So I get to work with loads of great students, engineers, and scientists to make different kinds of missions and systems work successfully. And we're all helping each other to explore the solar system. So now, of course, I think that space engineering is a lot of fun, but many different kinds of people participate in space exploration. Space really is for everyone. Maybe one day, one of you could be operating a rover on another planet, or maybe even an astronaut that goes to the moon. And so that's going to take me to the Junior Astronauts program. So I believe Jesse has information to share with everyone, but I'll quickly talk about that here. So the Canadian Space Agency is looking for junior astronauts. So what is the Junior Astronaut program? Well, it's to get Canadian youth excited about science using space. It's also to inform them about what careers and what it takes to become an astronaut. and it's to show how they can play a role in future missions to the moon. Um, now, the March 29th is currently the deadline for students to submit their applications. Now, there might be an update to that. I might not have
Yes.
all the current information.
Actually, just
But
really brief update, Matt. April 30th. So it's on their website now. They've just announced it recently because of all kids being at home. And so that's the new deadline, April 30th. Lots of time.
Perfect, perfect. So all the information about junior astronauts is available on on the Canadian Space Agency website. Now, take a look at the pictures here. All of these kids grew up to become Canada's current astronauts. So we have David, Jeremy, Jenny, and Joshua. So one day that could be one of you. So here is an activity that you can try, and I believe Jesse may have this activity posted as well.
Yep. So what I'm going to do for all our students joining in at home is junior astronauts. I've already made a link in the YouTube chat part of the program, so you can check that out. And I've also passed along a link to a past session where we walked through the entire Survivor Moon program with Dr. Gordon Ozinski, also at Western Space. So if you're keen to check that out, you can do that online, and it's free for all kids at home now. Anyone can do these programs and apply for a chance to win a visit to astronaut camp, which is awesome. So yeah.
Perfect, great. So I will just quickly run through this as well for anyone who hasn't seen this before. So you and your team member are astronauts from the Canadian Space Agency heading to an outpost on the near side of the moon. Your lunar capsule goes off course during your descent to the surface, and you land 50 kilometers away from the outpost. In your capsule, you have 15 items that could help you survive. Now, as a team, your task is to rank the priority of each of these items. What items do you really need to take with you in order to reach the outpost, which is 50 kilometers away? So there are a number of items that you can rank in importance. So let's just quickly go through them. So there's a stellar map. Now, could that be used for navigation on the moon? Can you use stars like you would on Earth? Would that be to your advantage? A case of dehydrated milk. Do you need milk concentrate in addition to food concentrate? Magnetic compass. Could astronauts use a compass on the moon? Does the moon have a magnetic field to be able to use a compass? There's also a signal flare. So what will signal flares do? And would that be helpful to wave down or flag down someone for rescue? You have a small fire extinguisher. So what could you use the fire extinguisher for? You also have a small inflatable raft. Now that might not be useful on the moon for any kind of aquatic activities, but the raft would be used when you land back on Earth, perhaps in the ocean. So you do have the raft with you. So could you use any parts from that raft? And would that be any use? Same thing with the parachute. So you're not able to use the parachute to descend on the moon because there's no atmosphere, but the parachute would be used for descent into when you come back to Earth. Now, what could you use the parachute for in this case to help you get to the outpost? You also have a portable heating unit. Now, so if you're on the near side of the moon, you might get some sun. So do you need extra heating, even though it is pretty cold on the moon? And you have a box of matches. Does the moon have any atmosphere with oxygen to burn a matchstick? Probably not. You also have 20 liters of water. Now, what do you need water for during again, it's a 50-kilometer hike. That's quite a long ways to go. You have 15 meters of nylon rope. So what could the rope be used for? Traveling or climbing or tying things together. And two 45-kilogram tanks of oxygen. Now, oxygen is useful for breathing. You may want to have oxygen on your hike back to the outpost. and there's a first aid kit, and a solar power FM transmitter and receiver. And there's also some food concentrates. So do the astronauts require food while trying to reach the outpost? So you have all of these items in your capsule, and you want to rank them. Which is the most important, and then which is the least important. So how would you rank these collection of items? So that was everything that I have today. And I did want to leave lots of time in case you have any questions about space engineering, CubeSats or satellites or rovers. So hopefully there's questions out there, and then we can go through those while you're working on your junior astronaut activity.
Fantastic. Well, thank you so much, Matt. And I love that presentation. I love the comparison of satellites to various animals. I've never seen that before, so that was kind of fun. All right, so we've got a few people watching on YouTube Live, so you guys have already let me know where you're joining from. Just type in some questions, and I'll pass along as many as I can. But I want to start with one from Grace, which is how many CubeSats are out there in our solar system right now?
So there are, I think there's some estimates that there's over 500 have been launched. So there are loads of CubeSats have been launched from Earth. They've been sort of around for around 15 years. These small form factor satellites, and they're becoming more and more popular, particularly with universities, as it's a lower cost entry to help teach and train students in space engineering and how to conduct space missions. And CubeSats are also used for testing hardware in space. And so if there's any companies that want to test out new types of sensors or computers or hardware, CubeSat is a lower cost way to test that before it's deployed on a much larger mission. And so most CubeSats have they're used in low Earth orbit or around Earth, but there have been some CubeSats that have left Earth's orbit. And so the most interesting ones so far were the Marco CubeSats, which went to Mars, and they were a one-time use application. And so these Marco CubeSats helped relay information during the Phoenix land, or not the Phoenix lander, the Mars InSight lander. So as the Mars InSight lander was landing on the surface of Mars, these Marco CubeSats were used as data relays so that the operators on Earth had more opportunity to receive data from the lander as it was descending onto the surface of Mars. So these CubeSats are now becoming more and more useful as we try to explore the solar system. And there's a few upcoming CubeSat missions to the moon, which will be able to orbit the moon, and they'll carry a single instrument, but they'll be able to do like a very low orbital pass around the moon and get much lower down, and take some get the data that the scientists are interested in. So most CubeSats are in low Earth orbit, but they're starting to go out into the solar system.
Fantastic, Matt. All right, if you want to come out of screen share so we can see you a little better when you're answering these,
Yes.
that would be great. That's okay. And a second question from William: is there a plan to clean up these satellites when they're done, or do they become space junk, and do they pose a risk to Earth if they stay in orbit?
So that's an excellent question. Yes, so there are now thousands of pieces of spacecraft, both currently active and from past missions that no longer are operating. So thousands of pieces of space objects that are in low Earth orbit or in orbit around Earth, and if there's too much of this debris in orbit, it could pose a challenge to launching new spacecraft outside of to get into orbit and launch new missions. So that is a concern. Now, what's great about these CubeSats and the CubeSats that we're operating is that they're at a low Earth orbit. Now, I mean, we think of space as being outside of Earth's atmosphere, but even even at the altitude of the International Space Station, there's still a very thin amount of atmosphere there. And so when we launch our CubeSat, it's going to be at an altitude where there'll still be a little bit of atmospheric drag. And so after about, somewhere between 6 and 12 months, the CubeSat will naturally deorbit and burn up in the atmosphere. And so there is there is a great concern about launching too many things into orbit. However, with our CubeSats and a lot of CubeSats material in space.
Fantastic. Thanks, Matt. All right. Grace wants to ask, how many times does it take to get these projects to work? The first time we send them, does it work, or do we have to send 50 and maybe only one gets up there?
So the history of space exploration is fascinating. If you look at the old Soviet Venus program, they used to just send spacecraft one after another, hoping that they would eventually work. And it took 15 or so before they were able to land on the surface of Venus. Nowadays, we try to impose more rigorous engineering processes and standards. So at the start of a project, we do what's called requirements engineering. So we thoroughly define what it is what is it that we're trying to do with the space system. What does that space system need to do? And then how do we ensure that we define what the be it the spacecraft or the rover, what does it actually need in order to work properly? And then as we're defining those requirements, we're also defining now, how do we test that? How do we ensure that, if we say, the spacecraft needs to be able to generate so much power, how do we test that to ensure that it will generate that much power? And so this is sort of the the back end of the space engineering process, where it's about properly defining what the space system or the satellite must do, and then also define how to test that to ensure that it does what we want it to do. And so through rigorous testing and rigorous standards, we are able to have a better success rate on the first try. Now, of course, there are instances where we'll launch something, we'll try to operate it, and then it fails. But those are also learning opportunities to help ensure that those mistakes aren't repeated again. So it's no longer the true trial and error of past space exploration. So there is a much greater rate of success.
Yeah. One of the things too that I find very cool, you talk about the Russians just sending things out and hope for the best. Now we're starting to reuse rockets, and this is something we're seeing with SpaceX, where they send rockets up and then the boosters come back down, so we can reuse them, which is going to radically lower the cost of a lot of satellite missions and getting people to spacecraft out in space, as opposed to the spacecraft on the ground, which we don't need rockets for. Oh well. All right. Another question from William: who controls these satellites? So you mentioned 500 up there. Who's actually making sure they're all doing what they're supposed to be doing?
So for every mission, we'll have its own operations team. And so for the CubeSats that my students are working on, they'll eventually be the ones that will operate them from our mission control center. And so they have there's software that they can use to talk to the spacecraft whenever it's passing overhead. And so we will send the commands to the CubeSat. The commands will be processed by the spacecraft, and we'll receive the data back. But that's all done on the ground, and so there will be teams, operating teams, dedicated to each of these spacecraft. And so that itself takes a lot of work and practice to make sure that when things are going well, we get to the information from the spacecraft that we want. But even more importantly, if something goes wrong, it's useful for the operating team to understand how to react and try to troubleshoot and problem solve, like what went wrong and how do we fix it. So, not unlike our Zoom connection going down and trying to figure out how do we restart that. So it's through loads of practice and teamwork, the operating teams are able to uh, you know be successful in ensuring that that they're able to get mission success.
Amazing. Well, thank you so much, Matt. And I like the reference to our Zoom session that have never been said before. So before we wrap up, is there a place where can we send kids that are tuning in to learn more about the work that you do, more about the work that Western Space is doing, and about the Junior Astronauts program? So I've put a few links in the channels already, but just to put it in words, where can we send kids?
So the Western University and its Institute for Earth and Space Exploration, there's a large outreach program, and there's a ton of materials and resources, and so you can go online. There's lots of activities available. There's also, it's a little on pause at the moment, but there are classroom outreach activities, but those materials are available. People can contact the outreach team for any resources or assistance. If there's any other questions about space engineering, I'm available to answer questions, and I know Jesse has my contact information. I'm always happy to answer questions. And so there's definitely loads of resources available. And what's great about space and space science and space engineering is the people involved are usually very passionate about sharing what it is that they do, and they're always willing to talk to kids that are interested in space, or adults that are interested in space. It's really about ensuring that everyone that's interested is able to participate, and because we like to share our excitement.
Amazing. I put my email address for Exploring by the Seat of Your Pants in the YouTube chat bar. So if you want to reach out to Matt, reach out to me first, and then I'll put you in touch directly. That's fantastic. And again, there are links to Western Space and to Junior Astronauts there, so you guys should all be set. Thank you so much for tuning in today. And Matt, thanks so much for joining us. We really appreciate you being here today.
Oh, great. Well, thank you very much for having me.
Awesome. Have a wonderful rest of your day, everyone, and bye for now, guys. See y'all soon.